This problem states that in a perfect fifth, the two notes have a 3:2 ratio. For example, 440 hertz and 660 hertz. The two strings, one of length 0.3 meters and the other of length 0.2 meters, are made with the same material of linear density 0.005 kilograms per meter. Part A is asking what should the tension in the two strings be to give the fundamental frequencies of exactly 440 hertz and 660 hertz. So the first thing I did here is just list out what we know and some of the equations that we have from this unit, as well as drawing a picture showing what that first harmonic is going to look like for the standing wave of the guitar. So we were given in the unit that velocity of string equals wavelength times frequency equals square root tension of the string over linear density. And with all those values, we're going to have enough to solve for the tension in the string for these two different strings. So it's good to keep in mind, and you can see this especially well in the picture, that wavelength equals 2L. So when we are going to be using the equations on the left, we're going to be plugging in 2L for wavelength. And that'll make solving it easier. So the first thing that you can see I did was plug in that 2L and rearrange the equation so we're solving for the tension in the string, and that gives us 4L squared times frequency squared times linear density. So the key thing here is keeping straight what values go with what equation. So for the 0.3 meter string, that goes with the 440 hertz. So once we plug in those numbers, we get 348.5 newtons. And then for the 0.2 meter string, we get 660, or they gave us that at 660 hertz, and we get the same tension of 348.5 newtons. So that's the answer for part A. Part B is asking how many beats would occur between the third harmonic of the 0.3 meter string and the second harmonic of the 0.2 meter string. So the key thing to remember here, and you can see these in the pictures, is that wavelength significantly changes for the second and third harmonic. So for the second, you can see wavelength now equals L, which is going to affect our tension equation to now make it L squared times frequency squared times linear density. And for the third harmonic, the equation is now 4/9 times L squared times frequency squared times linear density. So once again, I think the tricky thing here is keeping it straight what equation you're using with what values. So the problem tells us that we're doing the third harmonic of the 0.3 meter string. So that means we're going to use that third harmonic when n equals 3 equation for the 0.3 meter string, and that gives us the frequency is 1,320 hertz. And then for the 0.2 meter string, the new frequency is going to be found using that second harmonic equation, and that gives us that the frequency is once again 1,320 hertz. So the equation for beat is F1 minus F2. So essentially, this case, we're going to get that the frequency of the beat is 0. So these waves essentially overlap, and they aren't beating at all. So that's the answer for part B. Part C states that in an equal tempered scale, the notes would have frequencies given by 440 times 2n over 12, with n equals 0 for A and n equals 7 for E. By what fraction does the tension have to change to tune the string to the equal tempered scale? How many beats would occur between the third harmonic of the 0.3 meter string and the second harmonic of 0.2 meter string for the equal tempered tuning? So the key thing here, once again, is keeping values straight. So using what they gave us, the 440 times 2 to the power of n over 12, we can say that for when n equals 0, I said n equals 1, but it's supposed to be when n equals 0, we're going to get 440 hertz. And then for n equals 7, it's 659.255. So using those values, we're going to be able to figure out how tension will change. So Since frequency is the same for A, the tension in that string is not going to change, but because the frequency is clearly different for the string that is supposed to correlate with E, that tension will have to change. And we can find that change by kind of looking at the ratios of the tensions. You can see when you divide the equations of the tension for the string earlier that we saw for earlier with the new tension, everything cancels except for the tension and the frequencies. So we know the frequencies, so all we have to do is plug those in, and we find that the difference in those tensions is 0.9977. So essentially the tension in this new string is going to decrease by that amount. So we can go ahead and apply that, just multiply by that original tension we found, 348.5 times 0.9977, giving us 347.71 newtons being the new tension. So the frequency is now going to still be the square root of T, the tension of the string over L squared times the linear density, because we have the same case as the previous step where we're doing the second harmonic for this n equals 7 string and the third harmonic for the n equals 1 string. So yeah, we're going to use that same equation, giving us 1318.5 hertz. And since we're using these same equations, we can remember from the previous step that the other one was 1320. So whenever you find this new difference, you get 1.5 hertz between these two strings. So that means that the beat is 1.5 per second, 1.5 beats per second. So yeah, that's the answer for part C. Definitely the hard thing about this problem is, like I said, just keeping really straight what equations correlate with what values and all that. So the thing that really helped me was just being really organized with my work for this problem. But other than that, the math is pretty simple. So yeah, that's about it. Thank you for listening.